Polymers are macro-sized molecules of relatively high molecular mass which find extensive use in our daily life. Polymers are large but single chain-like molecules in which the repeating unit derived from small molecules called monomers are covalently linked. Structurally, they are characterized by many repeating molecular units which form linear chains or a cross-linked network. Polymers though बड़े material दे कुछ common examples plastic dishes, cups, non-stick pans, automobile tires, plastic bags, raincoats, television and computer cabinets, flooring materials ਅਤੇ biomedical materials ਅਤੇ surgical operations ਹਨ. In this chapter, polymers are classified according to their structure, strength and their properties. We will also be studying about their applications. Before going any further, let us discuss the learning objectives of today's lesson.
On completion of this topic, learners will be able to explain the terms monomer, polymer and polymerization and appreciate their importance. Distinguish between various classes of polymers and different types of polymerization processes. Appreciate the formation of polymers from mono and bifunctional monomer molecules. Describe the preparation, properties and uses of some important synthetic polymers.
Let us first discuss a few important terms. What do you mean by a polymer? Polymer is a compound of high molecular mass formed by a combination of small molecules called monomers. What are monomers? Monomers are small units which constitute the repeating units in polymers. What is polymerization? The process by which monomers are transformed into polymers is called polymerization. Let us now learn about that is classification based on source of availability. Polymers are classified based on their source of availability as naturally occurring polymers, semi-synthetic polymers, synthetic polymers. Let us first discuss about natural polymers. These occur in nature, in plants and animals and are very essential for life. For example, proteins constitute much of the animal body, nucleic acid control heredity at molecular level, and cellulose provides food, clothing and shelter. Starch, cellulose, protein, silk, wool and natural rubber are some examples of natural polymers. Let us now have a look at the second type of natural polymers, which are semi-synthetic polymers. Semi-synthetic polymers are derived from naturally occurring polymers by chemical modifications. Vulcanized rubber, gun cotton and cellulose diacetate are few examples of these kind of polymers. Vulcanized rubber is used in making tires. Gun cotton, which is cellulose nitrate, is used in making explosives. Cellulose on acetylation with acetic anhydride in the presence of sulfuric acid forms cellulose diacetate used in making threads and materials like films, glasses, etc. Let us now discuss the third type of polymer, that is synthetic polymers. Synthetic polymers are man-made polymers which include fibers like Teflon and Dacron, synthetic rubbers, plastics and PVC. Let us now discuss classification based upon structure. On the basis of structures, polymers are divided into three types. First, linear polymers. In these polymers, the monomers are joined together to form long straight chains of polymer molecules. The various polymeric chains are then stacked over one another to give a well-packed structure as shown on the screen. Because of the close packing of polymer chains, linear polymers have high melting points, high densities and high tensile strength. Some important examples of linear polymers are high density polyethylene, polyvinyl chloride, nylons, polyesters, etc. Let us now discuss the second type, that is branched chain polymers. In these polymers, the monomer units not only combine to produce the linear chain called the main chain, but also form branches of different lengths along the main chain as shown on the screen. These polymer molecules, because of branches, do not pack well. As a result, branched chain polymers have lower melting points, densities and tensile strength as compared to linear polymers. An important example of a branched chain polymer is low density polyethylene. Others are amylopectin, glycogen. We now come to the third type, that is cross-linked or three-dimensional network polymers. In these polymers, the initially formed linear polymer chains are joined together to form a three-dimensional network structure as shown on the screen. Only two cross links per polymer chain are required to join together all the long chain polymer molecules to form a giant molecule. Because of the presence of cross links, these polymers are also called cross-linked polymers. These polymers are hard, rigid and brittle. Examples are bakelite, urea formaldehyde polymer, melamine formaldehyde. Let us now learn about classification based on mode of polymerization. They can be classified as homopolymers and copolymers, addition and condensation polymers. Let us now learn about homopolymers and copolymers. So we first begin with homopolymers. Now how do we define them? As the name suggests, polymers formed from one kind of monomer is called homopolymer. Examples are polyethylene. We will next talk about copolymers. As the name suggests, polymer formed from more than one kind of monomer unit is a copolymer or mixed polymer. Example is Buna-S or styrene butadiene rubber is a copolymer formed from styrene and butadiene. We will next learn about addition and condensation polymers. So what are addition polymers? Addition polymers are formed when monomer units are separately added to form long chains without elimination of any byproduct molecules. These polymers are formed by reactions between monomer molecules possessing multiple bonds. Example is ethylene undergoes polymerization to form polyethylene. In this case, the empirical formula of the monomer and polymer are the same. Other examples are polypropylene is an addition polymer of monomer propylene. The addition polymers can be either addition homopolymer or addition copolymers. Both polyethylene and polypropylene are addition homopolymers because they are formed by the addition polymerization of only one type of monomer units. Let us have a look at other examples of addition homopolymers on the screen.
Let us take the first monomer, butadiene, whose polymer formed is polybutadiene. We also see here that if a monomer is tetrafluoroethylene, the polymer formed is polytetrafluoroethylene, also known as PTFE or Teflon. The third case shows vinyl chloride as monomer and polyvinyl chloride, also known as PVC, or polyvinyl chloride as polymer. Lastly, we take the case of monomer isoprene whose polymer formed is polyisoprene, which is also known as natural rubber. Additional polymers formed by repeated addition of two or more types of monomer units are called addition copolymers. For example, Buna-S is an addition polymer of 1,3-butadiene and styrene. Other examples of addition copolymers are Buna-N formed from 1,3-butadiene and acrylonitrile, butyl rubber formed from isobutylene and isoprene, Suran formed from vinyl chloride and vinylidene chloride.
We will next learn about condensation polymers. Condensation polymers are formed by repeated condensation reaction between two bifunctional or trifunctional monomer units, usually with the elimination of small molecules like water, alcohol, ammonia, carbon dioxide, hydrogen chloride, etc. And the process by which condensation polymers are formed is called condensation polymerization. For example, nylon c12 is obtained by condensation polymerization of two monomers, that is hexamethylene diamine and adipic acid, each containing two functional groups with the loss of water molecules. You can see on the screen the reaction which is taking place. Like addition polymers, condensation polymers can be either condensation copolymers or condensation homopolymers. The polymer nylon c12 discussed a little while ago was of condensation copolymer.
Have a look at some other examples of condensation copolymers on the screen. As you are seeing, terylene or Dacron is a polymer which is formed from ethylene glycol and terphthalic acid or its methyl ester. Alkyd resin is formed from ethylene glycol and phthalic acid. Bakelite is formed from phenol and formaldehyde. Melamine formaldehyde resin is formed from melamine and formaldehyde. And lastly, we have polyurethane, which is formed from ethylene glycol and toluene and metadiisocyanate.
Let us now discuss classification based on molecular forces. The applications to which a polymer is put depends largely upon its mechanical properties such as tensile strength, elasticity, toughness, etc. These mechanical properties in turn depend upon the intermolecular forces of attraction such as van der Waals forces, hydrogen bonds and dipole-dipole interactions between adjacent polymer chain. Although these intermolecular forces are also present in small molecules, but their effect is not significant in small molecules as compared to that in polymers. This is due to the reason that the magnitude of these intermolecular forces depends upon the size of the molecule and the number of functional groups along the polymer chain. Obviously, greater the length of the polymer chain, stronger are the intermolecular forces.
Depending upon the magnitude of intermolecular forces, polymers have been divided into four categories. Let us learn about the first category, that is elastomers. Elastomers are polymers in which the polymer chains are held by weakest intermolecular forces. These forces permit the polymers to be stretched. A few cross links are introduced between the chains to help the polymer retract to its original position after the force is released. This means that they are amorphous polymers having high degree of elasticity. They have the ability to stretch out over 10 times their normal length and return to original position when the force is withdrawn. These polymers consist of randomly coiled molecular chains of irregular shape having few cross links. When the force is applied, these randomly coiled chains straighten out and the polymer is stretched. Since the van der Waals forces of attraction between the polymer chains are too few and too weak, these cannot maintain this stretched form. Therefore, as soon as the force is withdrawn, the polymer returns to its original randomly coiled state. Thus, whereas weak van der Waals forces permit the polymer to come back to the original position when the force is withdrawn. The most important examples of vulcanized rubber are Buna-S or SBR, a copolymer of butadiene, and styrene, that is Buna-N, neoprene, etc. Highly vulcanized rubber containing 20 to 25% sulfur is called ebonite.
We will now learn about the second category, that is fibers. These polymers possess high tensile strength and high modulus because of strong intermolecular forces like hydrogen bonding, which operate in polyamides. These strong forces also lead to close packing of chains and thus impart crystalline nature. As a result, these polymers show sharp melting points. These polymers are used for making fibers. Examples of these kind of fibers are nylon and terylene, hydrogen bonding in nylon 6,6. We will now talk about the third category of intermolecular forces which exists in thermoplastics. In thermoplastics, the intermolecular forces are intermediate between elastomers and fibers, and the polymer chain has no cross links. These are linear or slightly branched chain polymers which are hard at room temperature, become soft and viscous on heating, and again rigid on cooling. The process of heat, softening and cooling can be repeated as many times as desired without any change in chemical composition and mechanical properties of plastic. As a result, these plastics can be molded into toys, beads, buckets, telephone and television cases. They have little or no cross links and hence the individual polymer chains can slip past one another on heating. Few common examples of thermoplastics are polyethylene, polypropylene, polystyrene, polyvinyl acetate, polyacryl nitrile, etc.
We now come to the last category of intermolecular forces which exists in thermosetting polymers. These are semi-fluid substances with low molecular masses which when heated in a mold undergo change in chemical composition to give a hard, infusible and insoluble mass. This hardening on heating is due to extensive cross-linking between different polymer chains to give a three-dimensional network solid. In nutshell, a thermoplastic polymer can be melted time and again without any change, while a thermosetting polymer can be heated only once when it permanently sets into a solid which cannot be remelted and reworked. Some examples of thermosetting polymers are phenol formaldehyde, that is bakelite, urea formaldehyde, melamine formaldehyde.
Let us now discuss classification based on the mechanism of growth polymerization. Nowadays, polymers are also classified on the basis of type of mechanism involved during the growth of polymerization chain. On this basis, addition polymers are also called chain growth polymers, since they are formed by repeated addition of monomer molecules to the growing chain carrying a reactive intermediate such as a free radical, carb cation or a carb anion. On the other hand, condensation polymers are also called step growth polymers, since they are formed as a result of stepwise condensation reactions. Children, we will now discuss types of polymerization. Two major methods generally used for preparing polymers are addition polymerization, condensation polymerization. Let us first discuss about addition polymerization. When the molecules of same monomer or different monomers simply add together to form a polymer, the process is called addition polymerization. The monomers commonly used are unsaturated compounds such as alkenes, alkadienes and their derivatives. This mode of polymerization can take place through formation of either radical or ionic species such as carboanions and carbocations. This process is also called chain growth polymerization. It involves the addition of monomer units of the growing chain by a chain mechanism. At each stage, a reactive intermediate is produced for use in the next stage of growth of the chain. Addition polymerization reaction are of two types. They are free radical and ionic addition polymerization, both cationic and anionic. Let us discuss about free radical addition polymerization. A variety of unsaturated compounds such as alkenes, alkadienes and their derivatives readily undergo polymerization in presence of a radial initiator, which is a radical generating catalyst such as dioxygen, benzoyl peroxide, acetyl peroxide, tertiary butyl peroxide, etc. For example, polymerization of ethene is carried out at high temperature of about 350 to 570 Kelvin and at high pressure of 1000 to 2009 atmospheres in presence of dioxygen or a small amount of benzoyl peroxide as radical initiator. These initiator molecules readily decompose on mild heating to form initiator free radicals. For example, benzoyl peroxide on heating produces phenyl initiator free radicals. The phenyl free radical thus formed adds to the double bond of ethene molecule to form a new and larger free radical. This is called chain initiating step. The new and large free radical produced in the chain initiating step reacts with another molecule of ethene to form another bigger sized radical. Repetition of this sequence with new and bigger radicals carries the reaction forward. This step is called chain propagating step. Ultimately, the growing free radical chain gets terminated by reactions which consume these free radicals either by combination or by disproportion. These are called chain terminating steps. About low density polyethylene. It is manufactured by heating ethylene to 350 to 570 Kelvin under a pressure of 1000 to 2000 atmospheres and in presence of a trace of oxygen or peroxide. This polymerization occurs by a free radical mechanism which is initiated by oxygen or peroxide. Polyethylene thus produced has a molecular mass of about 20,000 and has highly branched structure. This branching occurs due to hydrogen abstraction, as we will explain right now.
At the high temperature at which this polymerization occurs, the growing free radicals not only add to the double bond of the monomer but also abstract hydrogen from a chain already formed. This abstraction generates a few free radical center from which a chain can now grow as shown on the screen. These branched polyethylene molecules do not pack well and hence this type of polyethylene has low density and low melting point. That is why polyethylene prepared by free radical polymerization is called low density polyethylene.
Let us now learn about properties and uses. Low density polyethylene is a transparent polymer of moderate tensile strength and high toughness. It is chemically inert, slightly flexible and is a poor conductor of electricity. It is widely used as a packaging material in the form of thin plastic films, bags and insulation for electrical wires and cables, in manufacturing of squeeze bottles, toys and flexible pipes. Let us discuss now the second category of polyethylene, that is high density polyethylene. It is prepared by coordination polymerization of ethene. In this process, ethene, which is present in a hydrocarbon solvent, is heated from 333 to 343 Kelvin under a pressure of 6 to 7 atmospheres in presence of a catalyst consisting of triethyl aluminium and titanium trichloride or tetrachloride known as Ziegler-Natta catalyst. Have a look at the equation on the screen. The polyethylene thus produced practically consists of linear chains of polymer molecules. These polymer molecules pack well and hence this type of polyethylene has higher density of 0.97 grams per centimeter cube and higher melting point than the polymer produced by free radical polymerization. That is why polyethylene prepared by coordination polymerization is called high density polyethylene. Let us now discuss the properties and uses. High density polyethylene is a translucent polymer. It is also chemically inert but has greater toughness, hardness and tensile strength than lower density polyethylene. It is used in the manufacture of containers, buckets, tubes, housewares, pipes, bottles and toys. Let us now discuss commonly used nylon is nylon 610, which is obtained by the condensation of hexamethylene diamine containing 6 carbon atoms, and sebacic acid, which is a dibasic acid containing 10 carbon atoms. Let us now discuss uses. Unlike cotton fibers, nylon fibers do not rot, have high tensile strength, are tough, abrasion resistant, and somewhat elastic. These are therefore used in the manufacture of carpets, textile fibers, and bristles for brushes. Further, nylon fibers are so much stronger than the natural materials that these can be made much thinner. The availability of such a strong thin thread made possible nearly invisible women's stocking called nylons. Being tough, nylon is used as a substitute for metals in bearings and gears. Crinkled nylon fibers are used for making elastic hosiery. Let us now learn about nylon 6 or Purlon. Nylons can also be prepared from a single monomer having a potential amino group at one end and a potential carboxyl group at the other. For example, the monomer caprolactam on heating with water at high temperature, polymerization gives nylon 6. Caprolactam needed for the purpose is manufactured from cyclohexane. When caprolactam is heated with trace of water, it hydrolyzes to aminocaproic acid, which upon continued heating undergoes polymerization to give nylon 6. It is manufactured by most of the industries in India. It is called nylon 6 since the monomer caprolactam contains 6 carbon atoms. We now come to the end of today's topic on polymers. Let us discuss a few questions and answers to check our understanding. My first question is, define the term polymerization. The answer is, polymerization is a process of formation of a high molecular mass polymer from one or more monomers by linking together a large number of repeating structural units through covalent bonds. Next question is, in which classes the polymers are classified on the basis of molecular forces? The answer is on the basis of intermolecular forces of attraction operating between the different polymer chains. Polymers are classified into the following classes: elastomers, fibers, thermoplastics, and thermosetting plastics. My next question is, define thermoplastics and thermosetting polymers. The answer is, thermoplastics are linear polymers which can be repeatedly softened on heating and hardened on cooling, and hence can be used again and again without any change in chemical composition and mechanical strength. For example, polyethylene, polypropylene, etc. Thermosetting polymers, on the other hand, are permanently setting polymers. On heating in a mold, they get hardened and set and cannot be softened again. This hardening on heating is due to cross-linking between different polymer chains to give a three-dimensional network solid. For example, bakelite, melamine formaldehyde polymer. Excellent. Well done, students. So I hope that you all have enjoyed today's lesson. Thank you, students, for the attention you have paid in understanding these concepts. I hope you've enjoyed the lesson as much as I have enjoyed. ਅਗਲੀ ਵਾਰ ਇੱਕ ਹੋਰ ਨਵੇਂ ਵਿਸ਼ੇ ਦੇ ਨਾਲ ਮਿਲਾਂਗੇ। ਤਦ ਤੱਕ ਲਈ ਇਜਾਜ਼ਤ।